going to finish up experiment 3, at least the in-lab portion, so we'll be doing part 2 of experiment 3. You'll have a quiz. Always bring your calculators for calculations in lab and for the quizzes. And your report for experiment 1 is due this week, so you will be handing in your notebooks this week, turning in that report. This week, a reminder, I talked about this last week, but here's another reminder. On Friday, this week Friday, our chemistry seminar is at 3 p.m. instead of 4 p.m. So open lab is open from 9:30 a.m. to 2:30 p.m., not 3:30. Okay, so if you need to come into lab on Friday, it's closing at 2:30. So just keep that in mind. Next week, we're going to be doing experiments 5 and 6. The actual doing is experiment 6. So for those of you that get started on things before you come to pre-lab lecture each week, experiment 5 is discussing infrared spectroscopy. So we'll look at that in lab. So it's more about the technique, but the actual lab that you're going to do is experiment 6. Okay, so we'll talk about that again next week. And then in 2 weeks, which is fall break, but also in 2 weeks your experiment 3 report is due. Okay, so we'll talk about that a little bit next week as well. All right. So when you guys left lab last week, you have your trimeristin that you isolated from your nutmeg, and it should be in your drawers drying for this week. Okay, and so now we're going to carry that on to the next step. Couple things to be careful with. First of all, be careful with the organic waste. We're getting 2 layers in our organic waste, which is not good. So make sure that you're careful with the organic waste, not to get any water in the organic waste. The other thing is also make sure you're not putting any nutmeg in the organic waste. Okay. So if you find any remnants of nutmeg, don't put that in the organic waste. Now this week we're going to start with, we need to weigh our trimeristin from last week. Okay, so you need to know what that dry weight is, so you know how much you have to work with. The breakdown here of what you are going to need is for the reaction to form myristic acid. You need 0.7 grams to 1 gram of trimeristin. You don't, even if you have more, you don't want to use more than a gram because it doesn't really convert over to myristic acid very well once you use more than that. Okay, and it'll make the recrystallization more complicated. So you want to use somewhere between 0.7 and 1 gram of trimeristin. You are also going to set aside 0.05 to 0.1 grams of your trimeristin. Okay, and this you definitely want to make sure is your own trimeristin. All right, and we're going to use that for melting points, and we'll talk about that here in a little bit. If you don't have enough for the saponification reaction, so you don't have the 0.7 to 1 gram, a lot of times in lab we end up with people that have extra, and so we'll kind of in lab figure out who has more trimeristin that you potentially could borrow from and who has less and needs that. But usually it works out, balanced out, that some extracted more and can donate some, and some that didn't get as much can take the donations. Okay. What if you end up using or donating any trimeristin? Make sure you note all that in your notebook really clearly. Where things went or where things came from. Okay. But regardless, make sure that the trimeristin you set aside is your own. All right. And if you need a little extra for the reaction, that's fine. Okay. And like I said, we're going to talk about here how we use this for melting point determination for trimeristin. So this week in lab, for the reaction that we're going to perform is a hydrolysis reaction or saponification of an ester. And one common product that is made from this type of reaction is soaps. A lot of times are made, although more and more they're more synthetic thing, but can be made from the hydrolysis of naturally occurring fats. And so when we hydrolyze the ester, what ends up happening is we're gonna, so we have 13 carbons off of our ester. So we're gonna just, in general, kind of pretend our carbon tail here is this thing. So we've got a lot of carbon and hydrogen. And then we've got our ester. Once we hydrolyze it, we form some sort of salt, and this is water soluble, okay? And the way that it aligns is if you have, as it works for a soap, if you have like a little dirt molecule here, these tails do not want to be out in the water, okay? So they'll come around and hang out around the little bit of dirt. But this part that is soluble in the water wants to be out with the water, okay? So you end up forming what is called a micelle, where we have this hydrophobic interior that kind of carries the dirt, and the hydrophilic, what likes to be out in the water, exterior, okay? And so this is how soap works to get rid of dirt, all right? And it's by taking these esters and then doing this saponification reaction to make these salts that the soap is useful and does its job. So what we are going to do is a very similar reaction. We're also going to get sodium salt of fatty acid, and like I said, that saponification helps solubilize things that would not be soluble in water. So the reaction we're looking at, we looked at this reaction briefly last week, but I'll go through it again. Our experiment 3, saponification or hydrolysis reaction. Here is our trimeristin. We've got this triester, homotriester, because all the ester chains are the same, of our glycerol. So here's our glycerol, okay? And what we are going to do is we're going to use sodium hydroxide, okay? And you can do, with esters, you can hydrolyze them with acids or bases. We're going to use a base, okay? But we need 3 equivalents of the sodium hydroxide because we've got these 3 ester chains, okay? So it takes 1 sodium hydroxide for each ester chain to perform the hydrolysis. And our sodium hydroxide is in water. And then we're also going to use ethanol as our co-solvent, and we're going to perform this reaction at what is called reflux. So I'll talk to you here in a little bit about what is meant by reflux. So once we do this reaction, in our reaction mixture, we're going to have our glycerol, but it's not associated with our ester anymore. So we're just going to have glycerol out in the reaction mixture. And then we'll also have our 3 equivalents of our salt, okay? So it'll look kind of soapy in your reaction flask, and it should, because we basically have now made a soap, okay? So we will have our sodium myristate. So it's not quite the myristic acid yet. So at this point, we've got our sodium myristate and our glycerol. This is water soluble. So even during the course of the reaction, this is not immediately water soluble, but as the reaction takes place, you'll see the solid being converted over to the sodium myristate as more and more of that solid becomes soluble, and at the end of your reaction, then you should have everything will be soluble in the reaction mixture, okay? Then what we need to do is we've got to take our sodium myristate and be able to get our myristic acid out of that, okay? So does that salt look at all familiar to something else that we've seen before? Does that look like anything you previously have seen? Like maybe our benzoate salts, right? We had the same, it was a benzene ring here, but we had the same thing when we had the salts of our carboxylic acids for experiment 1, right? The same end here, basically, and it was that salt of an ester, or in our case, we made it from a carboxylic acid. They're both really closely related, okay? So how do you think in that, thinking about to experiment 1, how should we get our sodium myristate to convert to our myristic acid? What would be a good way to do that? Add hydrochloric acid, right? So that's what we're going to do. We'll add 3 equivalents of HCl, and then we will get our myristic acid out. Plus some sodium chloride, okay? And just like when we reformed our benzoic acid, this is not water soluble. And so this, once we add our HCl at the end of our reaction, you will definitely see a solid that you're then going to isolate with vacuum filtration, all right? Now it's really important that you keep in mind our stoichiometry throughout this whole process is not all 1 to 1 to 1, right? We start with 1 trimyristin, but we end up needing 3 equivalents of NaOH. We form 3 equivalents of sodium myristate. We use 3 equivalents of HCl, and we form 3 equivalents of our myristic acid, okay? So keep in mind the stoichiometry as you go through the process. Yeah?
What do you mean by equivalence? You didn't say it in that.
So just like back in Gen Chem, when your ratio was, like, you'd look at stoichiometry and you need one of these and 3 of those to make the reaction happen, that's 3 equivalents. So we need, if we had, say we have 0.1 mole of trimyricin, we'd need 0.3 moles of sodium hydroxide. So that would be the 3 equivalents. Everyone see that? Okay. So stoichiometry is really important for this reaction, all right? And keeping in mind the stoichiometry when you're looking at, when you're calculating yields and theoretical yields, it's really important to keep that stoichiometry there as well, all righty? Okay? So this reaction, probably maybe eventually, if we just let it sit for a while, would happen on its own, just sitting there at room temperature, but it's not going to work very well at room temperature. It's not going to work in your lab time very well at room temperature. So we need to use something called reflux to help it along, all right? And so reflux is a method of maintaining a reaction at a constant temperature. While being heated. And that constant temperature is the boiling point of the solvent for the reaction, okay? So reflux is a lot like if you have to make spaghetti noodles, okay? When you cook the spaghetti noodles, you're keeping that pot of noodles and water at a constant temperature. It's the boiling point of the water. Okay, and you keep it at that constant temperature until your spaghetti noodles are cooked, and then you drain everything off. So that's the same idea with reflux. We can keep a reaction at a constant temperature if we use the boiling point of the solvent. And no matter how much heat you throw at the reaction, as long as the solvent is present, it is not going to go higher than the boiling point of the solvent. That's as hot as it can get, okay? Now you can get it, you know, just like when you boil spaghetti noodles, you can get it boiling really rapidly and get it, you know, coming out of the pot because it's boiling so much, or you can keep it at a nice simmer and keep it under control. Same thing with a regular reaction. You can get it boiling really vigorously, but maybe it's not completely under control. But you're still at the boiling point of the solvent. So 2 things that are key to this, okay? You've got to boil the solvent, okay? But if you boil away the solvent, you will eventually lose the solvent and you won't have anything there to keep the reaction at a constant temperature. So you also have to condense the solvent, okay? So when you have a reflux, when you're using reflux to heat a reaction, you've got the solvent is boiling, but it is also condensing. So the boiling and condensing of the solvent will keep that reaction at a constant temperature. And that's what's involved with reflux, okay? But it's really important not only that it's boiling, but it's also condensing. So, in your lab manual is our basic setup for a reflux. All right? And we're going to set it up. It shows it set up on an iron ring. We have stir plates in all the hoods. So we're going to just put our stir plate on top of the ring stand, on the plate of the ring stand. Then you will be using the heating mantle. So you have not used those before. You'll be using your heating mantle And then you will put your 100 milliliter round bottom flask that it tells you to use with your trimeristin in it and your ethanol and your sodium hydroxide in here and a stir bar, okay? And then you want to clamp that flask so that it's sitting well, sitting down in the heating mantle, and make sure that that neck is nice and vertical, okay? Then we're going to put our condenser on top here. And usually you want to use your live egg condenser because you've got the best cooling with that. It's got the biggest jacket on it. So you're going to have the most water circulating through. You're going to have the best cooling with it, okay? So you put your live egg condenser on here. And then you also want to put a clamp here, but this is not like clamped on tight. You want it there to support it, and you want it there loosely, but you don't want it clamped on tightly, okay? And the reason for that is when we're done heating, we want to be able to raise that whole apparatus out of the heat. So we want it loose enough that it's just holding along the condenser, but not such that we can't move the apparatus up and down, okay? And then just like with our distillation, we had water in on the bottom and water out on the top, okay? So again, we're fighting gravity to push it up through the condenser and then out the top. So just like your simple distillation, you want to set this up next to your sink. Don't have it like way over to one side and the sink's way over here, because we've got to get the water back into the sink again, all right? Now the ohmite that you're going to plug in the heating mantle to is on the opposite side. So it is a little bit of a balancing act because you've got to have enough length for the cord to get into the ohmite, but then just make sure that you get as close to the sink as possible as well, okay? And so on your hoods, the plug that then has the switch and the dial, we're going to be using those this week, okay? And that is how we will control the temperature going to the heating mantle. So the numbers on the dial correlate to how much voltage we're giving the heating mantle. And we're not going to give it 100% voltage because then it would be too much. It'll get too hot, all right? So we control the heating with that dial, all right? So we'll probably start our heating at about 60 to 70, and then we'll just want to keep an eye on what's going on in our reaction and adjust it as we need to, okay? If it gets boiling too vigorously, we'll slow it down. If it's not quite boiling or not, barely simmering, then we'll crank it up a little bit, all right? The other thing that's really important is the top to our condenser is open. There is nothing on top of it, okay? So you do not want to seal off the top of your condenser because then you're heating a closed system, all right? And heating a closed system is bad because eventually we're going to build up enough pressure here that we need to release something, and so something will fly out of the system, okay? So no stoppers on top of reflux condensers, all right? We don't want a closed system. So you guys are going to set up your reflux apparatus, all right? And then we're going to go around and check them before you start heating, all right? Now with the heating, it's really important that you are heating it it tells you that you need to reflux for an hour. And once it starts boiling and condensing, that is when your hour starts, okay? So it's not the moment that you plug it in and turn on the heat. That's not when your hour starts. It starts when you actually start boiling and condensing, all right? So once you have been given the okay to start heating things, you want to get it plugged in, get things turned on, and then keep an eye on it and make sure you start seeing signs of it heating and progressing. You don't want it to sit there for a while and things aren't happening just because you don't have the ohmite turned up enough or you forgot to turn the switch on or something like that, because that is part of your heating time that's not happening, all right? So then once you are done with the reflux, then you're going to get everything cooled down to room temperature. We'll carefully pull, to help do that, you will carefully pull your apparatus out of the heating mantle and get it clamped above the heating mantle. It'll cool more quickly, and we want to get everything down to room temperature before we go on to the next step. So room temperature means you want your flask the same temperature as the bench top in the lab, all right? Be careful when you're handling the heating mantles. They're going to be really hot, okay? It was what was needed to heat this whole mixture to get it to reflux. So once you turn it off, it's going to take a while for it to cool down. So be really careful handling it. I would use the hot pad that's in your drawer to help handle it, so you don't burn yourself. It's just like, you know, when you make the spaghetti, the stove burner is going to be hot for a little while after you turn it off. Same thing with the heating mantle. So just be careful with that. Okay. Now that reaction that we performed, and this is in McMurray, the 7th edition, page 810. This mechanism I'm going to talk through, but it's not something that you're going to cover in lecture for, like you won't look at this until second semester, okay? But I'm just going to talk through it so you've seen the mechanism, so you're familiar with it, so then when you see it again in second semester, it's something that you've already had a first look at, all right? Our sodium hydroxide, so here's our ester, okay? So this is our long tail here, and then this part is our ester, which is attached to the glycerol, okay? The sodium hydroxide will attack the carbon of our carbonyl, okay? And then the electrons will kick up on our oxygen, all right? So then we end up with this intermediate species, all right? We've got this tetrahedral intermediate. But then what happens is the electrons of this oxygen aren't going to stay happy like this forever. So our electrons kick back down to our carbon, and in the process, we lose our OR prime, okay? And so that OR prime, in our case, is our glycerol. So we lose our glycerol off, all right? Then we've got our acid here. Everything looks happy, right? We've got our acid and we've got the salt of our glycerol. But what happens is this doesn't stay like this forever. Our alkoxide here ends up actually deprotonating our acid, all right? So we lose the protons from our acid go to, in our case, our glycerol, okay? So we end up making three myristic acids briefly, but then the protons from that end up going to our glycerol, and we end up with our sodium myristate and then our glycerol in our reaction mixture, okay? So when you stop the heating, this is where we're at. Then, once everything is cooled down, then we're going to add our HCl, and we'll reprotonate our acid, and that is what causes it to precipitate out of the reaction itself, okay? So then you'll have your solid back after you add the HCl that you will then isolate with vacuum filtration, okay? And that solid should behave a little bit different from the trimyristin. The trimyristin was kind of a nice grainy solid that filtered pretty easily. This is going to be kind of more soapy and more fat-like, this fatty acid, all right? So it's going to kind of be a little bit more slimy when you go to filter it. You'll see a little bit of a difference between this and the trimyristin that went into it, okay? So after you isolate your myristic acid, then we need to purify it, all right? And so just like in experiment 1, what did we use to purify our solids? Crystallization. So we're going to do the same thing here. And we're going to use methanol for our recrystallization, okay? We start with methanol, and then after you've got everything dissolved in methanol, you're going to use a little bit of water as a co-solvent as well, okay? But what we're heating is our methanol, all right? And the thing is, we only want this at about 50 degrees Celsius, okay? So we're not heating our methanol to boiling. We're just heating it to about 50 degrees Celsius. And the reason for that is our solids melt at really low temperatures. So if you get the solvent too hot, then you're going to melt your solid instead of actually recrystallize it. And so you get this oil in your mixture instead of actually dissolving the solid, okay? So our myristic acid, remember, it melts at about 54 degrees. Our trimyristin is going to melt at about 56 degrees. So that's why we've got to keep things at about 50 degrees. So you don't want to be any hotter than 50 degrees, all right? So you're going to heat your methanol to about 50 degrees, and then you're going to add your myristic acid and get that dissolved, okay? Oops. Okay, and then you'll let it cool and then follow the instructions. You're going to also end up adding water to it, okay? It talks about potentially needing a hot filtration. When you get to the point you've dissolved your myristic acid, if you have any questions about hot filtration, talk to your lab prof before you do it yourself, okay? Because this one can kind of be messy if you try and do it and don't keep it hot. You've got that slimy myristic acid kind of crashing out everywhere, okay? So if you think you need a hot filtration, talk to your lab prof before you do it, all right? And then you'll continue on with the recrystallization, let things cool slowly to room temperature, and then again isolate the solid with vacuum filtration, okay? So then you'll have your purified myristic acid. For the myristic acid, you also need to make sure you get a yield, which will need to happen after this has dried, okay? So probably at the end of lab this week, it will not be ready. You may need to come to open lab to get the yield there, all right? We will also need a melting point for the myristic acid. Our trimyristin, we're starting the lab period off with getting our yield, okay? And at some point, we should get our melting point as well, okay? And so if you have time in lab this week, you may be able to get it because your trimyristin is already dry, okay? The melting point for your myristic acid, you're going to need to remember to get it after it after the solvent has dried off, okay? So you've got this methanol water mixture that's going to need to dry, okay? But I talked about these two also having very similar melting points, okay? So just getting the melting point itself is not going to be good enough. We'll need some other way to confirm that your trimyristin and your myristic acid are two different solids so that you aren't getting out of your hydrolysis reaction just more trimyristin, all right? Thinking about experiment 1, what would be a way to prove that those two solids are different? Mixed melting point, right? But you'd be using it a different way than you did experiment 1. Experiment 1, you were trying to confirm the identity of your acid by doing mixed melting point. In this case, you're trying to confirm that they're not the same. So there's no standards for trimyristin or myristic acid to do the mixed melting point. What you want to do is take a little bit of your trimyristin, a little bit of your myristic acid, mix those together, and they should have a depressed and broadened melting point range, just like would have happened in experiment 1 if you picked the wrong acid, okay? So because they should be different solids, you do the mixed melting point to confirm that they are different solids, all right? So it's opposite of experiment 1. Everyone understand that? Good? Okay, and I would use, like you did with experiment 1, you used like 20 milligrams of each. Similar measurements is okay for this experiment as well, okay? And whatever you do, you want to just make sure you're using equal portions and you mix them, crush them really well together, like use your stir rod to crush things really well together before you take that melting point, all right? Now the other thing with the melting points, because you know about what temperature they should melt at, and it's low enough you don't have to do a fast melting point range, so you can just do a slow melting point range, all right? And you could actually do all three of them all at the same time. So you could do myristic acid, trimyristin, and the mixed melting point range all at the same time because there's 3 slots in the melt temps, right? So you could collect them all at the same time and not have to do one by one by one individually. Now for yield, remember that your myristic acid, that is an overall percent yield that you will end up calculating, okay? So you will have your yield in grams, and then you will go on and calculate a percent yield. The trimyristin, what you calculate beyond just the yield in grams is the percent recovery, okay? So remember here we're just comparing the yield to how much nutmeg we started with. This case, you have to calculate, okay, what is the limiting reagent for the reaction? What is the theoretical yield for this reaction, depending on how much trimyristin you use, and then what is that percent yield? All right. And all these calculations, make sure you show them clearly in your notebook at the end of the experimental, okay? So make sure it's all written out clearly. It's really hard to read reports that just have numbers flashed at you and you're not quite sure if they're right or not, or does it make sense for what happened. So make sure that you show all those calculations very, very clearly in your notebook at the end of your experimental. Okay. And then hang on to these guys, just like experiment 1, you want to hang on to your neutral compound and your acid compound till you get your notebook back from us saying, yes, you're okay, everything checked out okay. Same with these guys. Once you've got the yield and the melting points, don't throw them away. Hang on to them until you get your notebook back with a report for experiment 3 collected, and then you can get rid of them. And these can just be dissolved in acetone into the organic waste, just like your experiment 1 unknowns. Once you get everything graded, they can be dissolved in organic waste with acetone. Okay? All right. Questions at all with procedure? Good? Okay, that is all I have for this week. So,